the video lesson for the 7th grade Unit 6 test review over probability. I will go through the unshaded questions with you. After each unshaded question, I'd like for you to pause the video, go through and work out the shaded question on your own, and then bring it to your teacher for to be checked and to be stamped before you go on to the next question. So you'll watch the unshaded question with me, pause the video, work out the next question on your own before moving on. Okay, let's look at number 1. Malik draws a card from a hat and records the results. The hat contains cards labeled A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. All right, which of the following statements is true? Well, the first thing that I'm going to notice is that every one of the answer choices deals with vowels and consonants. Vowels and consonants. So it seems like that is what I'm going to be paying the most attention to. So first, I'm going to go through and circle all of my vowels. So let's remember that our vowels are A, E, I, O, and if we had a U, we would circle U. So we have 4 vowels. 4 vowels. Okay, and then I'm going to go through and I'm going to underline my consonants so that I can count those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So I have 4 vowels and I have 12 consonants. And what that tells me is that all together I have 16 cards. Now, if I had any duplicates, if I had 2 D's, for example, then I would need to count that twice. So each time they list a letter, that is a card that's in the hat. So we need to figure out which one is the most likely. Well, it looks to me like I'm more likely to draw a consonant than a vowel. So I'm going to go through and see what answer choices I can get rid of. A says drawing a vowel and a consonant are equally likely. Well, that doesn't look true because I don't have the same number, so I'm going to get rid of choice A. Here it says he is 1.666 times more likely to draw a vowel than a consonant. Okay, more likely to draw a vowel. Well, that's not true. I am less likely to draw a vowel, so I'm going to get rid of B. C says he is 1.666 times less likely to draw a vowel than a consonant. Okay, so that's less likely to draw a vowel. So I'm going to leave that one in there because I am less likely to draw that vowel. And D says he is 3 times as likely to draw a vowel as a consonant. So as I look at this, am I 1.666 times less likely to draw a vowel, or am I 3 times as likely to draw a consonant? So that's 2 different ways of looking at it. So in this case, I've narrowed it down to 2 answer choices. And I'm counting again. Let me double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I have 4 vowels. So in this case, I am 3 times more likely to draw a consonant because I have 3 times as many consonants. If I didn't actually have 3 times as many consonants, then that would be a good opportunity for me to look at the other answer choice that I still have available. Because I am also less likely to draw a vowel, but I don't know the exact number. If you have questions on this one, please come talk to your teacher. Otherwise, you're ready to go on to shaded number 1. Number 2 says, Mr. Matthews' class is doing an experiment. They rolled a fair 6-sided number cube, numbered 1 through 6, 2 times. So I'm rolling a die 1 time, and then I'm rolling a die the 2nd time. And it's numbered 1 to 6, just like a normal number cube. When they found the probability of rolling an odd number, then they found the probability of rolling an odd number first, and a number greater than 2 second. Okay, so we want to stop there, and we want to identify these 2 things. So I want the probability of rolling an odd number first. So my first roll needs to be an odd number. So I'm going to write odd under my first roll. And then I want a number greater than 2 on the second roll. Greater than 2. So I want greater than 2. They repeated this experiment 10 times, and we can see that because they've listed it 10 trials. Below are the results of their experiment. What is the experimental probability of rolling an odd number and then a number greater than 2? And we want to be sure to simplify always. So the first thing to notice here is that it is asking us about the experimental probability. Experimental probability isn't based on our formula. It's based on us being able to look at the data that actually happened when they did an experiment. And that's this. So we're not going to use a formula on this at all. What we're going to do is look at what actually happened. So I want an odd number first. Let's go ahead and write out what those numbers would be. That would be 1, 3, and 5. And then I want a number greater than 2. That does not include the number 2 because it says greater than, not greater than or equal to. So I want 3, 4, 5, and 6. So now we can go through and start crossing things out. In this column, I only want odd numbers. That means on the first roll, if I didn't get an odd number, then I'm not going to count it. So that's odd, odd. This is even. So let's get rid of that. 2, 2, and 4 are even. 3 is odd, so I'm going to leave that one. 6 is even. And then 3 and 5 are odd. So I have 1, 5, 3, 3, 5. Now we need to look over here at our second roll, and we want numbers 3, 4, 5, and 6. So 5 is good. We're going to get rid of 2. 3 is good. Get rid of 1. We like the 6, the 4, the 3, but not the 2. We don't like 1, but we do like 4. So now we've analyzed our results, and what we want is the experimental probability of rolling an odd number and then a number greater than 2. So in trial 1, I got an odd number and then a number greater than 2. So trial 1 was successful. In trial 2, I got an odd number, but then I did not get a number greater than 2. So we're not going to count trial 2. Trial 3, 4, 5, and 6 weren't even successful at the beginning, so I'm not going to count any of those, even though some of them gave me what I wanted on the second roll. Let's look at trial 7. I got an odd number, and then I got a number greater than 2, so I'm going to count trial 7. Trial 8 was not successful at all. Trial 9 started off successful, but then I didn't get a number greater than 2. And then trial 10 gave me an odd number and then a number greater than 2. So I'm counting 3 trials. Trial 1, trial 7, and trial 10 gave me both things that I wanted. So remember, the probability of both things happening, that's going to be what makes us happy out of the total trials. And remember, this is all based on the experimental probability, not based on math probability, the theoretical. So in this case, I have 3 trials that made me happy out of a total of 10 trials. I cannot simplify this, so that would be my experimental probability. You're going to do something similar on the shaded question. And when you're finished with that, you can get your stamp and then continue the video. Number 3. Thomas has 18 cards numbered from 1 to 18. He draws one card, then draws another card without replacing the first card. What is the probability that both cards will be prime numbers? And again, we have to simplify, even if it doesn't tell you to. Always simplify. So, I see that I have 18 cards. This is my total. I want to write down as much stuff as I can to help me out. So my total is 18 cards. It says he draws one card and then draws another card without replacing it. So that means that this is going to be just like our compound probability video where we were pulling out jelly beans and we wanted to get a green jelly bean twice in a row, but then it went down from 10 jelly beans in the bag to only 9 since it was not put back. So I'm going to find my probability twice, and what I'll do is set up my paper just like I did on the whiteboard the other day. This is trial 1. This is trial 2. And then down here is where I'll compound that probability. So let's do trial 1. The probability of a prime number is going to equal the number of primes, the number of things that will make me happy, over the total cards. Okay, so we need to stop here and talk about prime numbers. We do this in Mountain Math every week, but we've never really sat down and identified all of the prime numbers. So we know that we're going from 1 to 18. So let's list the prime numbers from 1 to 18 so that you can kind of start memorizing those. Because really you're going to have to just memorize them. Now, if you don't memorize them, you can actually figure it out by asking yourself, I don't know if this number is prime, so let me see if I can divide it by anything. And if you can, then it's not prime. If it can't be divided by anything else, then it is prime. So here are our prime numbers, and I would write this down if I were you and try to start remembering it. So prime numbers, we are going to count the number 1 as a prime number. And then we're also going to count 3, because 3 cannot be divided by anything else except for 3 and 1. 4 can be divided by 2, so we're not going to count that. 5 is not divisible by anything else. 6 is divisible by 2, and it's divisible by 3, so we're not counting that one. 7 is prime. 8 can be divided by 2 and 4. 9 can be divided by 3. 10 can be divided by 2 and 5. So our next prime number is 11. 12 is 3 times 4 or 2 times 6, so it's not prime. 13 is prime though. 14 is 2 times 7, so that doesn't count. 15 is 3 times 5. 16 is 2 times 8 or 4 times 4. So our next prime number is 17. And then 18, that would be 2 times 9 or 3 times 6. So that is not prime either. So if I go through my prime numbers, I see that I have 1, 2, 3, 4, 5, 6, 7 prime numbers. Okay, and that's just between 1 and 18. If we counted higher, then we would have a lot more. So we have 7 prime numbers. Let's go ahead and start calculating them. So the probability of prime equals the number of primes over the total, so that's 7 over a total of 18. And we just told ourselves that 7 is prime, which means I can't divide it by anything. Can't divide 18 by 7, so this is my probability, and it's already simplified. So we're halfway done. Now let's go over to trial 2, and we're going to say, what did I want to happen in trial 2? Well, I actually wanted the same thing, because it says the probability that both cards will be prime numbers. So here we have the probability of prime equals the number of primes over the total. Okay, same formula. But this time, I've already taken one card out. And remember, we always assume that the first trial is successful. So I pulled out a prime card already. So now instead of 7, I have 6. So I lost a prime card, now it's down to 6. And now instead of 18 cards, I have a total of 17. 6 can be simplified by, I can divide that by 6, or by 2, or by 3. But 17 is prime, so I can't divide it by anything. So this is simplified. The very last step is to come back over here. We're going to say the probability of prime and prime, or we could say the probability of 2 primes, equals, and that's the probability of the first one being prime, and times the probability of the second one being prime. So 7 over 18 times 6 over 17. And then remember, when we are multiplying fractions, we go straight across. 7 times 6 is 42. 18 times 17 is going to require me to do some math. So I'm going to come over here, and I'm just going to start multiplying. Make sure that you're doing this on your paper too. So 18 times 17. We want to make sure that we're neat, that our columns look good, that we're not being sloppy so we don't misread our work. 7 times 8 is 56. 7 times 1 is 7, plus 5 is 12. I'm going to put an X here and get rid of that 5 that I carried. 1 times 8 is 8. 1 times 1 is 1. And let's add. This is 6, 10, carry your 1, and 3. So 18 times 17 is 306. So this is kind of a monster, but we can start simplifying by saying, well, I know they're both divisible by 2 because they're both even. 42 divided by 2 is 21. I know that 300 divided by 2 is 150. And then 6 divided by 2 is 3. So this will be 153. And then I want to see if I can simplify any more. Well, I know 21 is divisible by 3 and 7. Let's check this one and see if it's divisible by 3. 153 divided by 3, decimal in the quotient, doesn't fit into 1, 5 times into 15, bring down that 3 and 1, so yes, that is able to be simplified. So let's divide them by 3, that's 7 over 51. Is 51 divisible by 7? I'm going to use what I know. This is us using our number sense. 7 times 7 is 49. So the next multiple of 7 would be 56. So this is fully simplified. So let's go back over what we did. This was kind of a long problem. We read the problem and we figured out that we wanted 2 cards that were prime numbers. So that's 2 trials. For trial 1, the probability of a prime number is the number of primes over the total, which was 7 primes over 18 total cards. Then we moved on to trial 2. The formula was the same since we were looking for the same thing, but now we had 6 primes out of 17 total. We multiplied the 2 probabilities together, and we just multiply straight across. We got 42 over 306, and we simplified a couple of times to get down to 7 over 51. So after you've done number 3 on your own, then you can unpause the video and go on to number 4. Number 4. Anthony is doing a project where he will draw a shape from a bag as shown below. He will do 30 trials. Set up a proportion that could be used to predict how many times he will draw a square. Then solve your proportion. So this is the same type of thing that we were doing on the pink cards with your partner. We're going to figure out the probability, then we're going to set up a proportion and solve it. So we know they haven't told us the probability of drawing a square, but we can figure it out pretty easily. We've got 1 square, 2 squares. So I know that the probability of getting a square is 2 chances out of, let's see, 4, 8, 12. 2 chances out of 12. And for the sake of simplicity, I'm going to go ahead and simplify this. That simplifies to 1 over 6. So now that I have that, I can start doing a proportion. So first I'm going to name my ratio. And remember, that's something over something. So total is always on bottom. And this is the number of squares. So basically, squares over total. Basically, for every, if I have 12 shapes, 2 of them will be squares. That also means that if I have 6 shapes, 1 of them should be a square. So we're just simplifying. We're creating equal fractions. And we'll see that at the end, we actually have an equal fraction as well. So after we've named our ratio, then we're going to set up our proportion. So that's line equals line. We start with what we know. We have 1 square out of 6 total, 1 over 6. And then the other information that we're given is that we're going to do 30 trials. So out of 30 trials, how many times should I expect to get a square? Remember, squares goes on top. The total, or the number of trials, would go on bottom. And then we just cross multiply and solve. So 6 times x is 6x. 1 times 30 is 30. I need to divide both sides by 6. And I can cancel those out. And I end up with x equals 5. So 5 squares. But if you want to make sure that you're not making a mistake, the next thing to do is to check. So I'm going to start with 1 over 6, or you could use 2 over 12. And then I'm going to plug in 5 and see if 5 over 30 gives me the same thing. So 6 times 5 is 30. 1 times 30 is 30. So that does work. It is proportional. And I know that my answer is right. So for this, we not only need to be able to get the right answer, but we also need to know what proportion would give us that answer. After you've done number 4 on your own, please bring it to your teacher for a stamp and then move on to number 5. Number 5 says you are flipping a coin 1 time. Draw a tree diagram to represent all possible outcomes. So this is going to be like the easiest question that you see on this review. All we have to do is start off. We're flipping a coin. So I have 2 possible outcomes. I have heads and I have tails. Heads and tails. And it says only 1 time. If I were flipping it a second time, then I would need things to branch off. I would have heads and tails here, and I would have heads and tails here. But we're not doing that. So think of this as your leaves. This is an itty bitty tree. And it only has like 1 little branch and 2 leaves sticking off of it. So this would be my tree diagram. We could also draw it this way and do heads here and tails here. So there's lots of different ways that you could see it. They can turn it any direction that they want to. So you're going to do number 5 on your own, doing the same thing with a die, and then take it to your teacher for a stamp. Number 6. Jeremy and Cameron are playing a board game. They record their first few turns on the tables below to keep track of where they are landing on the board. Based on these results, if Jeremy and Cameron both take 40 turns, compare the number of times Jeremy lands on free turn. Ooh, hello, puppy. You see the puppy. Say hi, Nika. Compare the number of times Jeremy lands on free turn and the number of times Cameron lands on lose a turn, and then explain in a complete sentence. So we're looking at two things, and we want to zone in on the important things in the question here. So my question says that I'm comparing Jeremy landing on free turn and Cameron landing on lose a turn. Okay, so Jeremy lands on free turn once, and he has a total of four turns logged in his table. Cameron lands on lose a turn twice, and his total logged here is 8. So the first thing we need to figure out is what it would be if we compared them. Okay, so I need to go ahead and work out two proportions. In this case, two proportions. It says we want to know what's going to happen if they both take 40 turns. So first we're going to name our ratio. And that's going to be what makes us happy, whatever that is. Okay, for Jeremy it's a free turn. For Cameron, apparently he wants to lose a turn, so that would make him happy. Happy over the total. Then we're going to set up a proportion. So here, for Jeremy, line equals line. I know that he lands on free turn one time out of a total of 4. So 1 over 4. And then I want to know how many times is he going to land on free turn out of 40 turns. Because up here it says they're both going to go 40 times. So if he keeps up with this kind of pattern, we should be able to figure out how many times he's going to land on that. So then we need to cross multiply. So 4 times x is 4x. 1 times 40 is, of course, 40. Let's divide both sides by 4. And x equals, let's see, that's 10 times. Okay, so out of 40 turns, Jeremy's probably going to land on free turn about 10 times. So let's go back over here and do the same thing with Cameron. So we've named our ratio. We're going to stick with that, happy over total. Let's set up our proportion. So he got what he wanted 2 out of 8 times. 2 out of 8. And I want to know the same thing that I wanted to know over here. How many times out of 40? So notice that this is the same. X over 40, x over 40. This is based on Cameron's chart, and I'm sorry, this is based on Jeremy's chart, and this is based on Cameron's chart. 2 out of 8 or 1 out of 4. So it's time to cross multiply. 8 times x is 8x. 2 times 40 is 80. We're going to divide both sides by 8. This is kind of a simple one. And x equals 10 times. So in this case, it just so happens that if they took 40 turns, Cameron would land on lose a turn 10 times, and Jeremy would land on free turn 10 times. The reason it's different here is because Jeremy, I guess he got kind of lazy and quit logging his results after 4 turns. Cameron kept logging until he had 8 turns. So we need to write a complete sentence to compare these. It says, compare the number of times that they land on these things. So Cameron and Jeremy will both land on their, what should we call this? Their preferred outcome 10 times. Or I can say they're equal. So make sure, what I'm really looking for is your explanation. Yeah, I want to see the work, but I want you to be able to analyze it at the end. So make sure you've got that complete sentence there when you go on and do number 6 on your own. Number 7. Candace has a stack of cards with equal numbers of squares, circles, and triangles. Based only on this information, circle all of the statements that are not true. And we need to make sure that we're circling the ones that are not true. So I'm going to go ahead and circle the word not true. And it says based only on this information. So we don't know how many of each one there is. We don't know how many times we're drawing them out. We don't know what's happening. All we know is that we have equal numbers. So we're equally likely to get a square, a circle, and a triangle. All of them have the same probability. So let's go through and circle the ones that are not true. Okay, the probability of a square is equal to the probability of a triangle. That's true, because all 3 of these are equal. So that one's good. We're not going to circle it. The probability of a square plus the probability of a circle plus the probability of a triangle is less than 1. Okay. This one can't work because if we add up the probabilities of all the things that we could get, it has to equal 1. So really this should say equals 1. So I'm going to circle this one because this is not true. If the probability is less than 1, then that means there has to be some other option, and there's no other option here. Okay, the probability of a circle is less than the probability of not a circle. Well, let's narrow this down. Okay, so this would be probability of a circle, and this is the probability of not a circle, so that's a square or a triangle. Well, if each one of these has the same probability, then this has a 1/3 chance, and this would have a 2/3 chance. Okay, remember our complements, right? It's the opposite. So yes, a circle would have a lower chance than not a circle. So I'm going to leave that one alone. That one's good. The probability of a square is equal to the probability of not a square. Okay, well that kind of goes against what this says. This would be a square, which is a 1/3 chance. And this would be not a square, is a circle or a triangle, which is a 2/3 chance. Well, that won't work. They're not equal. So this should say less than, just like over here. So we're going to circle D because that is not true. The probability of a circle plus the probability of a triangle is greater than 1. So a circle and a triangle, it can't be greater than 1. This would actually have to be less than 1 because we have to leave room for what? That other shape, those squares in there. So the probability of these two put together should actually be 2/3, which is not greater than 1. Let's get rid of this one. Circle that. Okay. And the probability of a triangle plus the probability of not a triangle is equal to 1. So we've got a triangle, not a triangle, that would be a circle or a square. This is 1/3, 2/3. Okay, so I remember that these are complements, which means that they're the opposite of each other, but also that they have to add up to 1, and they do. So it says it equals 1. That's true. So we're going to leave that one alone. So the 3 that are not true are these that we circled. So now you're going to do that similar question, number 7, on your own. Again, make sure that you're reading carefully and circling what's not true. Number 8, Kevin spins a spinner 35 times. All right, 35 times. That's our total. The table shows the number of times the spinner landed on each of 5 colored sections. They're red, orange, yellow, green, and blue. Kevin wants to predict how many times the spinner will land on yellow if he spins the spinner 60 times. Okay, so we've got a new total now, 60 times. What is the best prediction? Okay, so all we care about here is yellow. Apparently yellow is his favorite color. So yellow happened 14 out of how many times total? 35. And in fact, if we added these up, this would be 11 plus 14 is 25 plus 10 is 35. So he spun the spinner 35 times. Now, what's cluing me in here is this word predict. Okay, and prediction. Just like we did with the pink cards, anytime we're predicting something, it's a good idea to use a proportion because it's probably going to be a proportional relationship. We're using the information that we've already taken to predict how that would relate to a bigger situation. So let's go through this just like we would any other proportion. We're going to name our ratio. So I'm going to go with what I want, which is yellow, number of yellow, over the total. Okay, then we're going to set up our proportion. Okay, line equals line. Let's start with what we know. We know that the number of yellows is 14 and that the total was 35. So he landed on yellow 14 times out of 35. Let's go over to what we want to know. We don't know how many yellows. In fact, it says how many times the spinner will land on yellow. That's what we're looking for. If he spins the spinner 60 times, so that's our new total. We're trying to find a relationship here. So yellow over total, we're good to go. And now we're going to solve. I'm just going to rewrite this over here. 14 over 35 equals x over 60. And we start cross multiplying. 35 times x is 35x. 14 times 60. I'm going to have to work that out on the side. So let's come over here. 14 times 60. That's 0 and 0. We'll put an x here. 6 times 4 is 24. 6 times 1 is 6, plus 2 is 8. So I get 840. And nothing goes after the decimal point, because I had nothing after the decimal when I started. So 14 times 60 is 840. Now we divide both sides by 35. Cross out my 35s. There's nothing I can get rid of on the right side, so I just have to go ahead and divide. So I'm going to do this very neatly. Give myself plenty of space. Let's put our decimal up in the quotient before we start. $35 does not go into 8, but it does go into 84. So I'm going to start looking at what I know. Okay, well I know that 35 times 1 is 35. Let's try 35 times 2. 35 times 2 is 70. So that'll fit. Let's try 35 times 3. That's 15 and 10. Okay, so that one's not going to fit. So 35 times 2 gives me 70. We subtract and get 14. Bring down that 0. Now we need to go into 140. So I know 3 will fit. Let's try 4. 35 times 4. That's 20. And that's 14. So that fits perfectly. So 4 goes right here. And we already know that's 140. And I get 0 left over. So x is 24 times. So I've worked this out, but yet I still have to choose an answer. So it will land on yellow about 17 times. Nope. It will land on yellow 39 times. Nope. It will land on yellow 24 times. Okay, let's leave that one. It will land on yellow 14 times. No. But then there's more to it. It says since the spinner landed on yellow 2/7 of 35 spins, it would land on yellow 2/7 of 60 spins. Well, it didn't land on yellow 2/7. Okay, 14 is not 2/7. So it's 2 times 7, but not 2/7. So that's why that doesn't work. 39 times says the spinner landed on yellow 14 out of 35 spins. So it would land on yellow 39 out of 60 spins. That doesn't make any sense. This one says it'll land on yellow 14 times. Because it landed on yellow 14 out of 35, it'll be 14 out of 60. Nope, it's got to be proportional. This would mean that it would never land on yellow again. So let's go back to our first choice. It'll land on yellow 24 times. Since the spinner landed on yellow 2/5 of the 35 spins, it would land on yellow 2/5 of the 60 spins. So this is a proportional situation. 2/5 of 35, 2/5 of 60. C is the best choice here. So let's go back over what we did here. This was a long problem too. We found out that out of 35 times, Kevin landed on yellow 14 times. 14 out of 35. Then it wanted us to figure out how many times out of 60. So we don't know out of 60. We named our ratio, yellow over total. We set up our proportion. 14 out of 35 times will be the same as we don't know out of 60 times. We cross multiplied. We had to do some side work. And we got 24 times. So number 8 on your own will be very similar to help you practice this concept. And then you can go on to number 9. Number 9. Danny rolls a fair 6-sided number cube numbered 1 to 6. Circle all of the statements that are true. So, on the last one we wanted not true. On this one we want true. They can't make up their minds, can they? So I'm going to go ahead and circle the word true so that that stands out to me. He is more likely to roll a 5 than an odd number. So, I'm going to give you a hint. When you have things like this, you're going to have to actually sit down and figure these out. The good news is that you're so quick at this and they don't take very long, so you should be able to knock them out pretty quickly. So a 5, the probability of a 5 is 1 over 6 because there's only one 5. Do not put 5 over 6. That's what they want you to do. So if this number and this number are the same, you know that you've probably made a mistake because that's not going to happen very often. We have 1 5. Okay, the probability of odd is 3/6 or 1/2. Well, I'm more likely to get the one with 3/6 than 1/6. So is he more likely to roll a 5? No, he's actually less likely to roll a 5. Next, he's more likely to roll a multiple of 2 than a multiple of 3. So the probability of a multiple of 2, let's see. A multiple of 2, we've got 2, 4, and 6. So we've got 3 chances out of 6. The probability that it's a multiple of 3, we have 3 and 6. So there's only 2 chances. 3 out of 6 is a better chance, more likely than 2 out of 6. So this one, I'm going to circle. He is more likely to roll a multiple of 2 than a multiple of 3. Let's keep going. He is more likely to roll a composite number than a prime number. Okay, so here we go, back to our composite and prime. Remember, 1 is prime. Sorry, 2 is not prime. There we go. Let me start over. 1 is prime, 3 is prime, and 5 is prime. So, the probability of composite, that means that 3, the other 3, 2, 4, and 6, they just happen to be the same as the even numbers in this case. 3 out of 6. And a prime number, the probability of a prime number is also 3 out of 6. So they're even. He's not more likely to get either one. So that one's not true. I'm going to cross that out. Remember, we want the true ones this time, not the not trues. All right. He's more likely to roll an odd number than an even number. This is going to be just like that last one. The probability of odd is 3 out of 6. The probability of even is also 3 out of 6. So he's not more likely to get either one. It's a draw. It's a tie. Let's keep going. He's more likely to roll an odd number than a multiple of 3. Okay, well, the probability of odd, we already know is 3 out of 6. And we already know that the multiple of 3, we can come back up here. The probability that it's a multiple of 3, we have 3 and 6, so 2 chances out of 6. And he is more likely to roll an odd number because we have 3 of those and only 2 of these. So I'm going to circle this one. He's more likely to roll a number greater than 3 than a number less than 3. Be careful on these. It doesn't say equal to 3, so I'm not going to count 3 anywhere. Probability of a number greater than 3, so that means 4, 5, 6. 3 chances out of 6. The probability of a number less than 3, that's 1 and 2. Remember, we're not counting the number 3, so 2 out of 6. He is more likely, so I'm going to circle this one. And my last one says, he's more likely to roll an even number than a 2. Okay, the probability of even is 3 out of 6, 2, 4, 6, 3 chances. The probability of a 2, there's only one 2 available, so it's 1 over 6. Much more likely to roll an even number than a 2. So I'm going to circle this one. So we had to figure out, let's see, on this one we had 7 different answers and had to do 2 probabilities on each one. We did 14 probabilities in just a minute or 2. So do not hesitate to take the time to go ahead and figure it out rather than guessing. So please do the next one on your own, and then we'll go on to number 10. Number 10. Cindy rolled a fair 6-sided number cube, numbered 1 to 6, several times and recorded the results in the table below. For each comparison, write greater than, less than, or equal to in the blank. So, and I see that each one of these is comparing experimental probability of something to theoretical probability of something. Okay, so let's remember that experimental probability is what actually happens. So this is where we're getting our experimental probability. In fact, I'm going to write that over here. Our experimental comes from right here, this table. our theoretical probability comes from what we know. So theoretical, this is the math version. It's what should happen. So I'm going to list this here. I know that the probability of rolling in, the experimental probability of rolling an even number, well, the probability of even should be 1/2, right? 3 out of 6. That's theoretical. But let's look at the experimental probability. An even number. Okay, 2, 4, and 6. So I've got 1 plus 8 is 9, plus 1 is 10. So that's 10 out of, let's see, that's 4, plus 5 is 9, plus 8 is 17, plus 2 is 19, plus 1 is 20. 10 out of 20. So over here, the experimental probability is 1/2. And the theoretical probability is also 1/2. So I'm going to say that they are equal. Okay, same thing with the odd numbers. So let's look at those. Experimental, I have 3, plus 5 is 8, plus 2 is 10. 10 out of 20 total. That's also 1/2. That's my experimental probability. The probability of odd, theoretically, should be 3 out of 6, or 1/2. So this is also equal to. Okay, the probability of rolling a 6. Well, over here, it's 1 out of 20. And over here, the probability of rolling any number is 1 out of 6. So 1 out of 6, 1 out of 20. 6 is 1 out of 20. So is the experimental probability more or less? Well, 1 out of 20, that's a much smaller piece of the pie than 1 out of 6 pieces. So I'm going to say it's less than. Because this is 1/20th, and this is 1/6. Okay, the experimental probability of rolling a 3. Well, the experimental probability of rolling a 3 is 5 out of 20, which is 1/4. And the probability of a 3 theoretically is 1/6. So which one's bigger, 1/6 or 1/4? I'd rather have 1/4 of a pie than 1/6 of a pie. So experimental is bigger in this case. Okay, so it's greater than the theoretical probability. Okay, next we're talking about a 2. The experimental probability of a 2 is 1 out of 20, just like the 6. Really, really small chance. But the theoretical probability of a 2 is 1/6. It's always going to be the same. So I have a much lower chance with experimental probability than I do with theoretical. The experimental probability of rolling a 5. That's 2 out of 20, which is 1 out of 10. And you guessed it, the probability of a 5 theoretically is 1/6. Again, let's think about a pie. Would you rather have a piece of pie that's cut into 10 pieces or a piece of pie that's cut into 6 pieces? I'd rather have the 6 pieces because then my piece is bigger. So, experimental probability is less. 1/10 is less than 1/6. The probability of rolling a 1. This is 3 out of 20. And this is 1 out of 6. Okay, so that's hard to compare. So what I'm going to do is I'm going to do like when we're trying to figure out which fraction's bigger. Okay, we just find our cross products. So 1/6 and 3 over 20. 6 times 3 is 18. 1 times 20 is 20. So that means 1/6 is bigger. My experimental probability is less. In fact, you could really do that for all of these. Instead of thinking about pi, you could just do cross products and see which one's bigger. Okay? Rolling a 4, that's 8 out of 20, which is 4 out of 10, which is 2 out of 5. So I'm going to go with the 8 out of 20 just because I don't want to risk messing it up and making a mistake. I know that the theoretical probability of a 4 is 1 out of 6, just like everything else. So which one's bigger, 1 out of 6 or 8 out of 20? Well, 6 times 8 is 48. 1 times 20 is 20. So that's no contest. 48 is definitely bigger. So that's my experimental probability. So that's greater. So when you're doing this, don't get confused by all the words. Just sit down and really think about it. Compare each one. As you go through, if it's asking about a 3, figure out, okay, what's the experimental probability? What's the theoretical probability? And then just compare them. See which one's bigger. When you're finished with number 10 on your own, bring it to me for a stamp. I'd like to make sure that you really understand how to do this type. And then if you have any questions that you didn't get answered while you were working, make sure that you ask those questions then so that you can have them answered before you come in for your test tomorrow or on Monday.